Hey there, everybody. In today's video, I'm going to take you through a bunch of different time series models. We have a total of 7 that we're looking at, and we're just going to compare and contrast the ability of each model to learn on the data that's fed into the model and make predictions based on the learning capabilities of that model. So we have an autoregressive model, which is great for capturing relationships between observations and lagged observations, right? Time series, we're always looking at more recent events and more distant events and the lag between these, right? So what's happened between these events, right? We're looking at the exponential smoothing model. This one will assign exponentially decreasing weights to past observations. I like this a lot. I think what happens in the past is not, in the distant past is not as important as what has happened in the recent past. So I focus on the primacy and recency. If this is something that's very recent, that's something I need to be concerned about. That's something I'm more aware of and more alert for. What's happened 12 months ago or 24 months ago or several years ago isn't as important to me. So that's what the exponential smoothing model is going to do. ARIMA is autoregressive moving average. This combines autoregressive moving components, and we'll take a look at this. That's the ARMA model. The ARIMA, sorry, just noticed a mistake with the abbreviation. The ARIMA is just like the ARMA, but has an I for integrated moving average. Okay, the SARIMA is seasonal autoregressive integrated moving average. So these names are getting more interesting and slightly more complex, but this is looking for seasonal trends or changes in data. Certainly you'll see this around holidays. So Thanksgiving is an obvious one. Christmas too, where people's purchasing patterns are slightly different between Thanksgiving and Christmas time, right? And then the LSTM, long short-term memory. This is more of a sort of almost like a neural network. So learning like a human being would learn. You show them samples of things over time, and repeatedly, the human will learn. Okay, a cat is a cat because it looks like these 3 pictures of cats, and I will learn how. I'll learn that a dog looks slightly different from a cat when you show me several pictures of a cat. So it's sorry, several pictures of a dog. So it's more like learning like a human would using neural networks. So it's slightly more interesting, slightly more complex. Sometimes the LSTM outperforms the others, and sometimes it underperforms the others, right? So it really depends. The best practice is really to run all of these models over the data, check the output of each model, and then pick the model that runs the best, right? You don't want to just pick one randomly and say, I'm going to look at autoregressive or exponential smoothing or something like this. Like, you want to run all of these and then pick the one that performs best. So let's go ahead and click in this next cell. I'm going to share all this data with you guys as soon as I post a video. I always post a sample code so you can copy and paste it into your own Jupyter notebook. This is the view that you see right now. It's a Jupyter notebook, and you can run it as is. Of course, I'm making all of my videos very generic. I'm trying to illustrate the point, so I'm solving practical problems, but your problem almost guaranteed is going to be slightly different than my problem, right? So I want to make it very generic so you can copy and paste maybe 95, maybe 98% of this code, make a couple small adjustments so you feed in your specific time series data into these models, and then solve your specific problem. So it's going to be very practical solution, but very generic too, okay? So I just ran the code. Here's the output. This is Yahoo Finance. We're pulling in data for the last 6 months. We're going back 6 months in time. That's what this does relative to today. Okay, I'm looking at the date time now. I said go back 6 months, and this is SBUX data that we're looking at. And again, of course, this can be anything. This is time series data for stocks. This can be your data can be retail sales. It could be even weather forecast, right? Weather is a time series problem that's people are trying to solve all the time, right? So here's the data, 8/19, going back 6 months to 2/18. So we're in the middle of August right now as I'm doing this, and we go back to the middle of February, right? So we have our data, pretty simple, pretty straightforward. Let's plot a chart on this, see what it looks like. Control Enter to run it. Okay, Starbucks stock price. Okay, so it jumped up a lot. You see a huge bump in the price. I know what this is. They announced that a new CEO was just hired. The stock went up 25% in one day. The news came out last week. I forgot the exact date. It was like last Wednesday or Thursday of last week, maybe Tuesday. It was pretty recent. So new CEO steps in and the stock price jumps up, right? So could we predict that the new CEO is going to join the enterprise? No, there's no way of knowing that. But the data is going to be fed into the models, and the model is going to learn from this and say, okay, there's a big event that happened. How do we handle this? How do we digest this? How do we interpret this? And how do we use this to make predictions into the future, right? So we can't necessarily make a profit on Starbucks, but we can understand what happened in the past and make predictions about what's going to happen into the future. So here's all my models. I put this into a list. I load the libraries, or I'm calling the libraries for all of these models right here. Again, I'm going to share the code with the video, feed this into a list, and we're going to iterate through the list. Okay, Control Enter to run it. There's my models. Great. Let's just look at the training test size. I'm using 0.8. This is 80%. It's pretty typical to see 80% or maybe 70%. It could be 75, somewhat arbitrary. The more that you train it, the better the model is going to learn. But then the less data you have as a holdout set to do the testing on. Okay, so this is the training. The testing is going to be the part that's not held out. So you want to kind of balance it where you want a lot of training for sure, so the model can learn over all the nuances of the data over a long period of time. But you don't want too much training, because if you don't have enough testing, it's not going to be able to make very accurate predictions, or the predictions are going to be somewhat maybe diluted because you just don't have enough data. So usually 70% to 80% is a good benchmark for training. Okay, so let's run it to refresh it. Okay, we have the output. This looks fine. Okay, and this is where we are at this point. We're about a third of the way through the video today, the lecture today. So the data characteristics, pretty straightforward, very clean, very structured data. So it's all stock data. It's been refined, highly refined actually. So we're not going to see any errors here. If your data does have mistakes, missing values, you're going to have to treat those and handle those, or these time series models are not going to work. I'm picking this one because it's pretty easy to use, but you're going to have to backfill those, forward fill, use some technique. There's several machine learning techniques on how to fill in missing values. I'm going to post a video on that very soon. If you do have missing values, it's easy to interpolate those missing values and fill those in. Okay, and any kind of hyperparameter tuning, that's another option you can employ here for training the model. But it's up to you how to handle this, right? There's all different scenarios, there's all different cases for hyperparameter tuning. If these models are performing pretty well, you don't need to do this step. If the models are underperforming, you do need to employ some kind of hyperparameter tuning methods, right? So in this case, we don't have to do it. So I'm going to go ahead and create some empty lists, fill those with the data from the training and the testing of the model, and we're going to see what the output is. So again, I'm not going to get into all the detail. That would take an entire day, and I don't want to bore everyone here with all these nuances and details, but I'm going to post the code so you'll have everything. You can copy and paste it, run it on your machine, and see what the output is, okay? So here's the mean square error and MAPE. So with these, any kind of squared error is going to be higher. Anything that is squared is going to be doubled, right? You're double counting. So it's more affected by outliers. The MAPE is more of a percentage of an error, not an absolute error. So usually the MAPE is a little bit easier to interpret and to explain to your stakeholders and to your clients. So lower is better. I'm seeing 4.7s, 4.70, 4.74. So these are some pretty decent outputs here. These models, all 7 of these models, all 7 of these models are being trained and tested and performing quite well. Okay, I have some interpretation of the MSE and MAPE. Again, this metric is being squared, so any outliers are going to have a larger impact on this. This is probably the better of the two metrics. You can certainly use both. Probably both are better, but if you had to pick one or give more focus to one, it would probably be the MAPE. It's looking at the percentage of error, right? So that's, in a lot of cases, it's better, especially if you have outliers, right? Those outliers are going to spike up the results of the MSE. So let's refresh this. We'll get the chart. So now these are the MSEs. So it's a little bit easier, I think, to visualize this. I always tell people an image or a picture is worth 1,000 words, right? When you have a picture, you can say, okay, the ARMA, that's the moving average, and the ARMA, automatic regressive moving average, are performing the best here. They have the slightly lower MSEs than the other 4 models. And here we have the MAPEs, and I would lean towards the MAPEs. And again, as over the MSE, and again we have ARMA and ARMA performing just slightly better than the other 4, right? So you have 3 top performing models here. Let me refresh this view. Okay, we've got that. Then we can move down to, and this right here is just taking all the models, again, looking through and trying to find out if there's anything else that we needed to do here. So far with the top 3 models are ARMA and ARMA. I think we have 3 models that we can go with. All are performing pretty well. This now is making predictions into the future. Okay, so based on historically what's happened, we can try to anticipate what's going to happen next with the stock price for Starbucks, right? Or for anything, right? If you're looking at sales of retail items or weather patterns, this is how you're making your predictions into the future and understand what's going to happen next. So this right here is the lowest MAPE that we've seen so far, 2.62. So again, lower is better. This is really the top performing model right here. So let's do one more exercise here. Plot the results so we can see, again, a picture is worth 1,000 words. So here's the AR model. You can see the actual stock price and the predicted stock price, pretty close, right? And the predictions are coming from this prior step over here. And here's the results printed out. So these are the next, what we would expect to happen next, right? Over the next several days, the stock price of Starbucks should be pretty close to this pattern. Now, if there's another exogenous event where I wouldn't expect another CEO to be hired within a 2-week time frame here, but if there's another major event that impacts Starbucks, it could be some kind of political upheaval in a country where Starbucks grows a lot of its coffee beans or sources its beans from. It could be a shock to energy prices if oil jumps up. There could be other exogenous events, but barring all that stuff, these would be the prices that we'd expect in the next about, how many days we're looking at? 26 to 34. About 10 days or so. This is what we would normally expect, right? All things being equal. And then we can see the actual and the predicted. Actual is in blue and the predicted is in red. And all these stocks are, all these models, at least the first 3 are performing pretty well and giving us results that are meaningful, and we should pay attention to this, right? This is pretty important. Okay, so that's pretty much it. Time series models, we looped through 7, got the performance of each, made predictions with each, and plotted each one. So hopefully you learned a thing or two. I think this stuff is pretty cool. I think it's pretty interesting, very useful in the real world. And that's pretty much it. Thanks for your time today, guys. Have a great day. Bye.